This tutorial is dedicated to the Pinecone. It will be our case study for discovering how to achieve this Phyllotaxis paneling, manipulate panels, and how to manipulate data in the tree. We're in Rhino and that's our Pinecone. Everything starts from this curve, third-degree curve with 5 control points. So the first thing will be to import the curve in Grasshopper. Then we'll hide it. Now we need the shape. We'll take the endpoints, move in the Z direction an axis, better this one. Maybe can put 10 here so you can see it. From this point to this, we build a revolution surface now. That's the curve and that's the axis. So that's the base surface for our definition. Now how to get Phyllotaxis shape? We'll use the Phyllosurface component. The parasticky numbers is a couple of 2 consecutive Fibonacci numbers. There's this index Fibonacci component which returns, we get a slider. So let's get the surface into it. A boolean toggle true tell the component it is a closed shape. Now, yes, 2 and 3. Now we could try to get into the data. What we want is 6, and that's the reason, because the 2 numbers that correspond to this index are 8 and 13, and these are exactly the numbers that we can find in nature on a pinecone. In fact, that's a study on pinecone shapes, and turns out that nature's rule respects these 2 Fibonacci numbers. We have exactly 8 spiral clockwise and 13 spirals counterclockwise. We need a parameter for building the faces. How many faces do we want for each spiral? So we'll use a range that goes from 0 to, let's say, 500 the maximum. As an output, you see we had 501. When we deal with steps, we always have an element more as an output. To fix it, we'll set an expression x minus 1, and then we have 500 elements as an output. Now a few less, 540. And then in order to make everything more interesting, we'll also use a graph mapper with the Bezier, and we connect the range into it. Then we have our parameter, and our shape is far better now. We can work on it a little bit more. We can work on the top, and we can get the shape more smooth also on the bottom. And we have a more interesting pinecone. So as you see, it's really not hard to achieve this kind of shape. And if we would like to just to make a render of it, that's not that hard. Working with mesh is fun, and with Weaverbird we have very nice tools like this one. We could, for example, set these two a frame and a window, and then join the meshes in this way, and we will have a pinecone, a nice pinecone. Anyway, let's suppose that we are working on this shape because we are making a study for a facade or a skyscraper or anything built in reality. Then we would like to study it on CAD, on surfaces. And in any case, we can take advantage of this Phyllotaxis component using this output in a different way. We can get the boundaries, and then explode the curves, and you see we'll have as a result segments and vertex grouped face by face. Once we have a data tree organized in this fashion, we can easily use it in order to build some surfaces. And we'll do that with prune tree component, which is here. Now we're going to use vertex. You see, there are a group of 4 vertices. It means that they are 3-sided faces, and there are a group of 5 vertices, which are 4-sided faces. And we will keep all branches with 5. This way we will eliminate all branches with less than 5 elements. Then we will do the same here. We'll do the same here. And we'll set 4. Now we have the faces separated. 4-sided faces, 3-sided faces. Very well. We can now keep going with call index. That's because the first and the last vertex are the same, and we don't need this repetition. We have to remove the 4th element from each list of this tree, and then remove the 3rd element from each list of these other 3. Then we'll simplify, and we're ready to make a polyline again from the triangular faces, which we're going to hide everything here. See, we have now only some triangular faces, and we'll have to say that they are closed. Let's zoom in it. There are really few faces. Now we can build surfaces on it, and it works very well. In order to treat the other three, we're going to use list item and pick each vertex out from the list. So 0, that's good. Now that we grouped all the vertices in this way, we can use this component for point surface and easily build every face at once, all the faces at once. Now, why I've used this method instead of the previous one? The reason is that for four-sided faces we are no longer sure that the faces are planar. That's why this component will not work. We can check it just making a copy and hiding this and trying to build polylines. That's well for polylines. We have closed polylines, but we cannot get surface out of them because they are not planar. That's why we are forced to use this other method. Now, having planar panels is very important because we have to design flat panels in order to make a model feasible in reality. So now we will see together how to get planar panels. We get back to the Phyllo surface component, to our meshes. We go on mesh tools and face normals. We have the center and the normals for each face. Now we need a plane. We'll use plane normal, and we'll connect the normal as the Z and the centers as the origin of the planes. We now have a plane for each face. Then we can use the vertices we created before and take it in a parameter. Now let's take a look to the data. We can simplify here, and let's take a look at here. We can, I think, simplify also here, but then we'll have to graft also here. Now this way we have a plane for each branch. Very well, we are ready to use the plane closest point, and we'll feed the planes here and the points there. Now let's hide everything and check what we get. Let's hide this and this and this two. Okay, now we have our points. And we'll use it in order to rebuild polylines out of them. Remember that we still keep our structure in the data tree. So the points are grouped face by face, and that's very important. Now we have the faces. Now we have the polyline, sorry. We make the polyline, and now we are pretty sure that those polylines are planar. In fact, our boundary surface works very well. So let's hide the point. Once we do that, we could take the center, can take out the centers of the faces, and we can also manipulate this geometry. Let's see, we can scale and move it, and move each faces. We'll use a slider here, the center, and the geometry. That's good. Then we could also move these faces along the normal direction. So we'll get an amplitude component, drag the vectors, and then use a slider. We'll have to let's see how the data looks like. Okay, maybe we have to simplify, and we'll have probably to graft also. It's fine. Then we're going to move this geometry on these vectors. It's very good. Why we had to graft? Because here we have this kind of data tree. We have a surface for each branch, and so we have also to have a vector, a normal vector for each branch. Well, once this done, we can hide the surfaces. We'll then use this component, the wrap edges, for extracting those edges. We'll also always simplify. And then we'll use these segments in order to build the faces in between the panels. Let's see. Okay, you have to simplify these two. Finally, we use the ruled surface component. That's A and that's B. We're ready to join the BREP over here and hide so let's take a look at what we got. Bake, oh sorry, let's bake grouping everything. Okay, so we have surfaces there, and we are sure that all panels are planar. Okay, we have almost finished. To make a visualization of the Pinecone, let's get back to meshes, and then a weaverbird, join, flatten everything and join the meshes. Then we'll get these loop subdivision component. Level of smoothing 2, side everything, and let's connect it. So there it is. Now we can bake it. It's a closed mesh this way, and we got a nice smooth Pinecone out of our definition.